So in terms of our unit on magnetism and electricity, electromagnetism, it's part of nature. They're two sides of the same coin. You can't have one without the other. When you have an electric current flowing, you generate a magnetic field. And if you remember from yesterday, what was the key thing? A lot of weird math, but the two big ideas. How do you get an electric current from a magnetic field? You just have a magnet sitting there? No, it's got to what? It's got to change. You have to have a changing magnetic field, and you generate an opposing induced field. Okay? Exactly. To balance out the energy there. So the electric current that's induced creates an opposing magnetic field to conserve energy. Now, the other thing that you got to learn then is, if you had to add another keyword in, opposing, changing, and then the third thing I would add in is perpendicular, sideways. It's kind of weird. Okay? And the analogy is kind of like this, that if you want to push an electric charge, say this is like an electron with a magnet, if I take a big old bar magnet, whatever, up to it, I can't actually push it directly. It won't move in the same direction. It'll end up going sideways. Okay? It's like weird. But that's just how it works in nature. I got my little chair here I'm trying to push. And if this was an electron and I'm a magnet and I'm trying to push on it, it'd be like I'm trying to push on the chair and then it starts moving like sideways. Like, woo, it's kind of weird. But that's what happens, okay, in nature there. So there are three right-hand rules we're going to use. There's a whole bunch of variations, and some people like to come up with specific rules for a specific situation, like a left-hand rule and all that. I like to keep it simple, okay, to try to help understand the basic ideas. So the first one is called the grip rule right here, where if you have a current flowing through a wire, okay, you guys remember what the symbol I stands for? I stands for what? I is for electric current measured in amps. You take your thumb for your right hand, you point it in the direction of the current, and then your fingers curl in the direction of the magnetic field, B. And notice that the magnetic field is perpendicular to the wire. You see that? So magnetic field lines will flow in concentric circles perpendicular to the wire. Why is that useful? Because in real life, things happen in 3 dimensions, and you need to know which way the fields and forces are working. Most of us, like, not a big deal. We just, whatever, turn on my radio, activate the power locks, lower the window, whatever, right? But if you're designing the car, you don't want, like, the doors to unlock when you want it to lock, or the locks to push sideways and pop your door apart. It doesn't make any sense, okay? So understanding these basic fields and directions and forces is important. So one way to kind of notate things in 3D is we can do what's called the X and dot notation. So if you think of like an arrow flying through the air, like this, I'll just sketch this off to the side. If I look at it head on, then it would be like a dot, like the tip of the arrow is flying in your face. This is coming out of the page because we're trying to draw in 3D. And then if you think of an arrow flying into the page and you look at the tail feathers, that would be like an X, okay, like the tail feathers going into the page. Okay? So let's look at it this way. What if I had the current, this wire, flowing out of the page towards you? Then which way would the field flow, if you think about it? So if I take this wire and I tilt it so that I is coming out of the page, then let's do the right-hand rule, right? If the current's flowing at you, then the magnetic field's going to go which way? Clockwise or counterclockwise? It's going counterclockwise, exactly, okay? And then let's say I want to get the magnetic field now to go clockwise. What would I do then? All I would do is I would have the current go which way now if I want to go clockwise? Have it go what? Into the page, right? If they reverse the current so that now I goes into the page, the electric current. So if you're like, designing a motor and you want to be able to reverse it, if you reverse the direction of the electric current and apply the right-hand rule, now the magnetic field will flow clockwise. You see that? In 3D there. Okay? That's the first right-hand rule. It's called the grip rule, like you're grabbing onto a wire or you're climbing a fire pole or whatever. Okay? Next, if we take that wire and we bend it into a loop, which we do all the time to make an electromagnet, so you intensify and have a really strong magnetic field, then the field lines get concentrated in the center. We create what's called the loop rule. And now we kind of flip around what our finger and thumbs are. Now your fingers curl in the direction of the electric current. Your thumb is the direction of the magnetic field. Okay? So if we wanted to kind of notate this on the page here, see how the current is coming out of the top of the screen? I could denote that with my tail feather and arrow tip notation. So out of the page on top of the coil would be a dot, like the tip of an arrow. Into the page on the bottom would be like an X. So I could kind of denote that in 3D. So in this case, which way is the magnetic field flowing? in terms of my right-hand rule for the coil right-hand rule? Is it going left to right? Which way is the field flowing? It's on the diagram, right? It's going to the right. How could I get the current to go, the magnetic field to go the other way? I just reverse the direction of current, right? So instead of having it go out of the page on top into the page on the bottom, I have it go the other way, right? Yeah? Make sense? Okay? Is this weird? It's kind of weird, right? Because you normally don't think about fields and 3D and all that there. Okay? So quick question. Go ahead. So great question, right? The difference between these two is they're actually the opposite. Where here, your thumb is the direction of the current, your fingers are the field. On this one, your fingers are the current and your thumb is the field. Okay? So all it is if you take a wire and you bend it into a coil, then the field lines circle around the wire and they end up concentrated in the center. So it's just a way to find the main direction of the field inside a coil of wire. We'll just keep it simple, okay? By the way, do you have to memorize all this stuff? Nah, okay? I would just put it on your note card so that you can apply it on the concept checks and then on your exam there, yeah? Okay? Finally, this is the one that's tricky, where people get a little confused sometimes. This is called the right-hand rule with the palm method instead of the British Fleming method there, yeah? So if you like the yo-yo homie way, I'm okay with that. I won't be offended, okay? But I'm not that coordinated. I just like to do the palm method, okay? Here's how it works. Your thumb points in the direction of the charge moving, the velocity, okay? Or another way to think of it is it's the direction that the charge moves, like a proton. Let's think of a proton here. If it's moving, that's like the electric current. So that's easier for some people. Instead of thinking it as velocity, you think of it as current. Your fingers point in the direction of the magnetic field, and then your palm is the direction of the force, like you're pushing it. Okay? So some people, they like to memorize it using this mnemonic. To understand magnetic forces and fields, you got to do a little fib. Okay? Not like you're lying or anything like that, but F is for force. Okay? I is for the direction of current, and B is for the field. Got it? So on test day, I'm totally okay with people writing on their hands, okay? You get a little magnetism tattoo. And it always cracks me up on magnetism test days when I walk by either our classroom or one of the AP physics ones. I always know when people are doing magnetism stuff, okay? You're not crazy, it's just that's how you figure it out. So let's do a simple example here, right? If I have a proton, a positive charge, okay, and I want it to move, okay, let's say it's coming out of the screen, this way, it's coming out of the screen, and there's a magnetic field going to the north, it's going to feel a force then, which way? To the what? To the left there, okay? To the west, or whatever, if you want to think of it that way. Okay? So in real life, when would you ever use this kind of thing? Simple example is an old-fashioned TV screen, okay? Now we have all these flat-screen TVs, but in the old days, you guys remember, right? You're not that young, right? What did it look like? Big old tubes, right? And actually, we used to have one, and they finally got rid of it. And I actually had to pull an old monitor out of the trash when we did the color thing. And then on Monday, I'll set up, again, you can try trashing it with a magnet and all that, just so you can see how it works, yeah? So if you recall there, when we did color, you guys took that magnet, right? What happened when you shoved it up to the screen? Do you guys see that? The colors all freaked out. You guys remember that? Lots of fun there, right? And all it is it's a cathode ray tube. You suck out all the air in there, so it's like a vacuum tube, and then you shoot a beam of electrons at the screen to paint it. And how do you move those beam of electrons? You got to use a magnetic field. But what's weird is if I want to push an electron to the right or left, I can't push it directly right or left because it ends up moving perpendicular. It's kind of weird, right? Like I'm trying to push it with a magnet up, and it ends up, right? This is kind of weird, and it's coming out of the screen at me. It ends up going sideways. It's like, huh? It's a sideways force. Think of it that way. Okay? Still don't get it? Let me help you. The best way to learn is by application. So another way to think of the right-hand rule is in real life, we use a right-handed system. If you think about it, we live in a 3D world. So in math, you guys already know this, usually x goes which way? X is to the what? To the right. Which way is y? Y is usually what? Up. And then now we want to go 3D, right? Z. Okay? So if you think about it, x, y, z is a right-handed system, where x is your thumb, y is your fingers, z is your palm. So z is going to come which way? Out of the screen, right? So why is this useful? If you're in that pre-engineering class where you do CAD, Okay, are you like into computer graphics and all that? You have to think in 3D. Okay, so this little simulation is a way to think in 3D. So normally x is to the right, y is up, and then z is coming out of the screen there. Okay, and in fact, this is a magnetic field simulator. If I run this here, if I shoot an electron into a magnetic field, z represents a magnetic field. It doesn't get pushed up; it gets pushed sideways. It's like totally bizarre. It ends up going in a circle if you don't change anything. Okay, so it's kind of weird there. But anyway, the point is, in real life, we can rotate things. Oh my goodness, crazy! Okay, so how do you not get disorientated? How do you keep things consistent? You use a right-handed coordinate system. Let me show you. Let's do an example really quick. Let's be insane. Should we be insane? Let's make x go a different way. Scandalous. Which way should we make x go? Instead of x going to the right, let's turn it. Let's have it go, pick a direction. Oh my goodness, let's have x go, I heard someone say something crazy, down! That's like illegal. That's okay, x is going down. See that? Let's make y go another way. Which way do you want y to go? Left. Okay, let's have y go left. That's nuts. Okay, so which way is z? Okay, so in order to not get confused or disorientated, so you know which way is up, down, left, right, a right-handed system keeps it consistent. Let's try it. Okay, x is which way? Down, right? Y is which way? To the right? Yeah, or to the left? See, I'm all disoriented, right? So which way would z be then? Boom. Z would be what? Z is now into the screen. Okay, so I'm going to do my little tail feather notation like that. Or if I can draw in 3D, which is very hard for me. This requires immense brain power on an afternoon. Ugh. I was trying to draw in 3D into the screen. Ah! Okay, you see that? So in other words, we can visualize things in 3D. How do we do this? We had x going which way? Down. Y was this way. And then z was actually, oh, I actually can't rotate this enough into the screen there. Okay? But anyway, it's a way to not lose your orientation in a 3D system. Okay? So, enough about right-hand rules for x, y, z. Let's do it for magnets. Okay? So how about this? Let's try the first one here. Okay? Find the force on a proton. So we have a positive charge here. What is B for? B is for the what? Magnetic field. And the little x's mean it's going what? Down into the page. You see that? And we want to find force. Okay? Force is your palm. B is into the page. Oh, we're missing something, which is I, the direction of the current or the velocity. So you know what? This one is a trick question. It's not going to feel anything because there's no velocity. It's not moving. No force because no velocity. Psych! You're like, why'd you do that? Well, I wanted you to realize you have to track three things, okay? So as long as you have any 2 out of the 3 quantities, you can figure it out. So let's do one where you have 2 out of the 3, okay? So this is our second practice one, okay? Where you're going to find the direction of velocity on this proton. So here we have a proton, a positive charge. It's getting, let's see, pushed into the page, okay? Because there's some kind of force acting on it from a magnetic field that goes to the right. So how are we going to figure this out? Tell a little fib. F-I-B, okay? So go ahead and hold up your hands and do it. That's the only way you can learn, okay? I know it looks weird, but if you just sit there, you're not going to learn how to do it. It's not natural at all, okay? So think about it. F is for force. Which way is the force? Into the screen, okay? So what's weird is this proton is actually shooting into the screen. Isn't that weird? Okay? The magnetic field is which way? That's your fingers, okay? It's to the right, okay? So your thumb then is the direction of the current or the velocity. So this proton is getting shoved into the page and it's moving which way across the field lines? It's actually going which way? It's going up, okay? This is the direction of the velocity. You see that? It's a sideways force, okay? It's kind of weird, right? In order for an electric charge to experience a force from a magnetic field, it has to move across the field lines, perpendicular. It's a sideways force. So you shoot a particle going up across the magnetic field, it ends up getting shoved into the page. It's kind of weird, okay? Why would you ever need to know this? Most of us don't need to, okay? But if you want to make your TV work right, your power locks, the motors to lower your windows, you don't want your windows going random directions, okay? That'd be weird. You want to lower your windows and then it comes sideways toward you. Ah! Then you got all confused, okay? Let's try another one. Now we're going to find the direction of force. But this one's weird. It's on a what? It's on a, not a proton, but a An electron. What the heck is an electron? What's the difference between a proton and electron? Instead of being positively charged, it's what? Negatively charged. Now, some people, they like to use what's called the left-hand rule. It's the same exact thing, but use it for an electron. I don't like to do that. You know what I like to do? I like to keep it simple. Let the lunch bell go. Hungry people, no problem. And ironically, a bell, you got to use the right-hand rule, okay, to get that electromagnet to go. But anyway, you want to use your right hand, and all you do is flip it. That's all, okay? Because if a positive charge goes one way, a negative charge just goes the other way. Remember on the circuit lab when you guys hooked up your meter wrong? You just got a negative reading? Same idea there, right? So let's try it. Hold up your right hand, and we're going to try to figure out the direction of force. That's the palm. We don't know that. F-I-B, okay? So which way is the magnetic field? It's flowing which way? It's going out of the page, okay? There we go. This is going to get kind of awkward. The velocity, or the current, is going which way? Down, okay? So it's going down, out of the page. So which way is the force? Your palm. It's going to the what? You see that? It's going to the left, and that's for a proton. So for an electron, it's going to go which way? Electron's going to go to the right. Okay? The force will go this way. Got it? That's your force there. If you're all confused, it's because you're not used to thinking about it in 3D. Also, normally you don't worry about it. Normally you just turn on your computer, let the hard drive spin, start your car, activate power locks, etc. Okay?